I will just mention that the reason why we do show and tell first is so that people who bring smaller children, particularly in the summer, can take them home and not have to go sit through the talk, which sometimes can go over the little kids' heads. Okay.
So this is for you, Wayne. This will be an example of navigation, okay?
Okay.
I've got the Nito Pyros here. And I've navigated around and I've created this map. You can see the map here, right? Let's see. Oh,
Be right back.
You want to plug it in?
no, I don't. That's dangerous. Okay, can you see it? Okay. There's actually a map.
Table is the best
Okay,
location.
nothing up my sleeve.
Did you save the map, Camp?
This is a nav map, dude. The robot shall now attempt to shall navigate to that door. I point and click 2D nav goal, and I'm going to drive him right out the door. Point, press, drag, mouse up, and here he goes.
Now, for those who aren't aware, he's running Rob's Argus and allows you to communicate with this robot. And by having a map, you can then say, okay, go to this location and now plan your path through the map to get there. And it should do obstacle avoidance too.
Yeah, I'm using the, and I'm going to set my goal a little closer. I may have to put a few waypoints in there because he seems to be ignoring me. But you see the path planning coming all the way down. You see Ryan there walking up behind us. So let me just set that goal a little closer if you don't mind, so I can get this navigating done. Point, press, and drag, mouse up. And you see, I saw two lines there. He's thinking about it. The robot is turning, and he is headed towards the goal.
This could be it.
It did it. It's done.
This could be it.
You folks are easily amused. Okay, let's take it a little further here. Okay, 2D nav goal. Hello, Steve. Okay, how are you? Okay, so here it goes a little further. Oh, this is the Nito BotVac D series. It's a vac. This one's not a vacuum cleaner, but generally it's a vacuum cleaner. It sells for about $400. The feature is it has a LiDAR, laser radar. There's one laser in there. It spins. It takes 360 snapshots and thereby creates a radar map. And you're able to, with ROS, use that to make sure it doesn't do the what do you call teleport? Make sure it doesn't do the teleport. Have you ever seen that in RViz where it teleports?
That's what happened. We've got it at the Connect Challenge.
Anyways, here comes the robot.
It's pushing.
It's trying to go that way. Is it getting through there? You can see the path planning going on. And I'm going to break away in a minute because we've probably got some other show and tells.
Yeah, that'll help. That'll help move it.
Yeah, he should have navigated around that. You see the inflation, the cost map inflation. There's the blue around the obstacles that gives it a little extra distance to navigate around. Anyway, so again, let me help him out. I'm going to help him out. I'm going to help him out. I'm trying to rescue him. Here, actually, let me try. Give me one more chance, okay?
I don't think so.
All right. How much more time do I have?
2 hours.
Huh?
Hours.
Okay, I'm going to set him in this corner now. Settle down, settle down. I'm really going to do some navigation here. Okay, so I do my pose estimate. I tell him that he's over here. And now you can see the local cost map kind of sort of matches up. Let's point, press, and drag another goal so he goes a little further. And you'll see him localizing here. Sometimes he gets into the whirling dervish. Right? Spinning around. That's how it localizes. Actually, since this robot has 360-degree vision, he doesn't really need to spin, so it's kind of a sideshow. But you see here he's going towards the goal. Okay. Yeah, okay, get my finger out of the way. So this is RViz. I meant to say, yeah, but what I'm using here, this graphical tool, is RViz. It's the ROS visualizer, okay? And so the Raspberry Pi's inside there, and we've got and it's telling the bot vac what to do through the USB API. And so we use the G mapping to create the map, save the map, 2D nav to navigate within it. And I'm just going to do one more navigation here. Wayne? Hello, Wayne. Is that an example of navigation?
We'll see if it can make it to the wall. I've been hassling Camp about this
Greg?
for a long time.
You're not helping, Greg.
Major map before we got here.
Show it glued on.
Yeah, you create the map, you drive around and create it. Here comes the whirling dervish. He's relocalizing, but he'll pick it up. He'll pick up the trail and go on. Anthony?
Be nice.
If you succeed, it'll come into camera view.
So you see him hugging the wall there. Questions?
I can't really camera view.
3 cheers for Camp. Camp's been trying to do this for a long time. It's not easy.
Thank you very much.
Yeah.
Can I be third? My battery's probably not going to make it.
Okay, so you'll come next.
Wouldn't you want to go sooner if the battery's dying?
Well,
Where is your robot?
He just needs this.
I see.
This is my HDMI.
Vision system.
Here we go.
Okay, good.
Enjoy it.
Okay, so I recently joined Greg's NASA Sample Robot Return Challenge. I don't know if I got the words in the right order. Are we still looking for more members for help, or I don't know.
I'm always open to people with good technology and ideas.
Okay, but I made a commitment. I promised I would show off some stereo vision range finding and object detection, which is what first thing before you can go bring back an object is you have to find it and recognize it.
During the last challenge, failed move.
Yeah. So basically, you have to have a stereo pair, and this was taken with 2 cameras, just 4 inches apart. On a real robot, it's always a problem because the robots are shaking, and if you don't have global shutter cameras, none of this works. So on the robot that I was working, I had the Minori camera, which is a single USB, 2 separate cameras, but it takes left and right separately. So the robot had to stop, wait till it stopped shaking, then get the 2 images for it to actually work. So that's a hardware problem. I'm a software guy. And basically, you click on an item, and it will find the object, find the corresponding object in the right image, do some computations and tell you where it is and how far away. Obviously, corners are really easy, so it's like that bottom corner there. And you'll notice over here it found the corresponding image. And the debug output, the bottom line shows distance of 12.75. Let's pick some other, here's some hard things to do. Like if you just pick the middle of the carpet, it seems, well, I guess the carpet might be textured enough to have found the corresponding section. And saying 14 feet away, I don't know if that's correct.
Well, given the corner was farther.
Well, for textures like that, it's kind of hard to see because if it's a uniform texture, and here's a good example, things that are obvious, like say the corner right here of the railing. And it finds a really good match over there, so its distance is saying 17.5. Yeah, in feet. Like here's like a black thing on the tree, and there it got the crosshairs pretty good. And that tree is about 7.28 feet away, but let's pick somewhere else on the tree. Found it pretty well. And that's 7.39 feet away. Now let's pick something hard, like,
Way in the back, the tree way in the back.
okay, like here's in between the leaves of the tree. Do you see this little window right there? Let's try that. So let's click in the middle of that window. And it did find it over there. And debug output says that that's 85.0 feet away. Now that's probably going to be give or take a few because the accuracy is based on how many pixels differential there is between the two images.
Try the, just above the landing on the first or second step up on that second landing where that tree kind of is clearly, you know, that little bush is like moving all around.
Oh, where it's occluded?
Behind the tree to the right.
Behind the tree to the left of the tree.
To
Where?
the left of the little shrub tree that's sticking up over the railing.
Oh, this right there?
On the steps.
On the steps themselves, but just past the first landing.
Oh, here's
Off
some
somewhere
failure
there.
modes. For example, see the yellow flowers? Like if I click this yellow flower group, it seemed to find that one pretty good. There was another like this flower. Yeah, see, I clicked in this flower, but it matched up with that one instead. Because they're similar, and it's basically which one has the minimal error. So in that case, it would think that that flower is, let's see what the debug view says. It's saying 14 feet. No, it's thinking it's 102 feet away because it's cross-eyed. The flower that I got is 14 feet away. And let's kind of verify that by picking a different flower. Let's do the second one. Yeah, I got the second one. Wait a minute. Now here's where it's going to fail. Like, see this area right here, the bottom elbow of the railing? There's no corresponding place, so it's going to fail. And it just kind of found a place off here in the dirt that it thinks that's the minimal error, but basically the error is high enough, it realizes, this is not a good match.
Is this open CV at the base, or what is this?
This is all, and there's that flower right here, and let's hope it's closer than the tree. Yes, 5.15 feet away. So basically this is the start of the vision system for the NASA return. So the idea is when we find an object, and it's going to be like a purple rock or a white foam with a hook in it sample, stereo vision, exactly.
Purple rocks.
Against the green Martian grass background. So it makes purple stand out. And that way we get the information, not only how far away is it, but you can see with the X and Y offsets, you can use that to easily calculate, is it above or below me, or how many degrees to the right do I have to turn to face it? So that's pretty much it.
Is there any way to estimate the errors? The error?
Yeah, the error is being printed out. For example, min error, it's some number, but let's scroll up to where it was cross-eyed and see what the error rating was. Most of the errors are in the, and I don't even know what the units are, it's basically just the sum of the errors of the image patch that it's trying to match.
So which software are you using?
This is all my own software. Not using OpenCV. I started the first prototype with OpenCV, but it was extremely slow for object detection, so I wrote my own object detector. This is pretty much real time. Really quickly, I'll show you, this is the edge detector algorithm, and basically, wherever you see bright lights here, it knows that's something important. So trying to click in this black area here and find a corresponding match, it's going to ignore it and say, sorry, I'm not even going to bother doing the calculations. But in this area here, you've got a lot of texture, especially look at if you follow the railing, there's these nice lines that you can follow, and then it will get a lower error score. So then it knows that this is a real object and not just like the carpet. Yes?
Can you sort of expand this by generating an artificial horizon and then doing like a cost map for obstacle avoidance?
I have not done that yet. But you could do an artificial horizon and do that. I didn't think initially that that might be even needed, because if you can just...
Some of the problems if you're on a slope, right? You're basically assuming that the camera's flat and level.
It doesn't really matter because even if the camera were tilted, it gives you, here's the distance and the rho and theta relative to my camera. So if you rotate the camera and these pictures were rotated, it would give you the proper offset relative to where the camera is. So you can rotate the camera any which way you want, and it will still give you the accurate position and distance of the object.
I'm thinking about using it for mapping. And if your map, you know, you're assuming that everything's in the horizontal plane, but the robot's tilted, you're looking off at different angles, so the distance is going to be incorrect.
It'll still get the right distance. For example, if you look at objects that are near the center of the image, that's looking straight on. But if there's an object above it or below it, like this flower at the bottom or even way up at the top, that window that's 85 feet away, it doesn't really matter if you're on a slope. Okay, we're going to move on.
One more question.
Can you quickly describe the pipeline?
Oh, the pipeline is grab the image, do my magic. When you click on the mouse, it finds what it thinks is an object, mostly based on color and a quick filter. Then it tries to find the corresponding object of a similar color and shape in the opposite image. And then it, based on the pixel offsets, computes its vector and distance.
Do you have any hardware acceleration like an FPGA or anything, or you just do it on the
Nope.
processor?
Nope, it's culling pixels that don't count very smartly. That speeds this up over OpenCV. Because OpenCV will give you a Z-depth map for pretty much every pixel. And I'm only really looking at 1,000 pixels in this particular image, and most of them are the hot spots that you would see here. So it finds the nearest corresponding hot spot. So smartly not doing work that you don't have to do is the secret to getting this fast. So, and more questions, talk to me afterward.
So Mark, you ready, or do we need to go to the next? Move on.
I think that I'm ready.
Okay.
Okay, this thing has been gutted royally since the last time it was here, but this was an entry that I'm getting ready for a competition called Robo Magellan, which every couple times a year gets played at various places like yeah. So it's not doing that right now. Instead, I picked up an $85 LiDAR unit, and I've got it set now so it's only going to be rotating and not driving forward, because this camera doesn't go down to the floor. So I figured, let's not have a lot of fun and have it fly off the table. So what this thing does is it tracks me here, and it looks at me, and then if all goes well, and I didn't screw up the parameters, yeah. So it's basically trying to track me and rotate around and follow me. And if I was on the floor and everything was enabled, it would of course come towards me or go away from me. So the idea is I can have it follow me around like a little dog, because my wife won't let me have a dog, see. Yeah, I gotta watch this carefully because we're on the table here. But it's got ROS operating system, and it's got my own proprietary marktoys.com servo controller encoder board thing. So I put DF robot motors on it now, like 265. Now it might be getting confused by the table also, because it's got about I told it don't look at anything farther than about 1.5 meters away, and then don't care about anything too close either. So now it's back to me, okay? So that's kind of what it does. It's got a little display on it. It's got some nice little drivers and stuff.
What camera is that?
This is a Raspberry Pi 2B. It's the camera is actually not hooked up right now, but I was using it on FiddlerBot, one of my earlier robots. I plan on putting the module I use here to broadcast over ROS. You can output video to a web page and pick it up and show it on a web page. I did that on a prior thing with a little guy I have called FiddlerBot. He's going to have all that stuff if he doesn't fall off the table. Yeah. Oh, and also he has a time vortex. Huh?
Yeah.
That's what I'm talking about.
Hypnotizing.
Yeah. All right, so it'll be around later if you want to ask any. Yes?
Is that the Get Surreal interface to the LiDAR?
Yes, so the LiDAR is an $85, because I wasn't fast enough to pick up one of Camp's at the last thing, but this is an $85 eBay special LiDAR, and that is the Get Surreal. Also, there was a thread on the, I don't know where that guy was located. I don't think it's local, but there was a thread about hooking up this kind of setup onto a ROS node. It's using the standard X11 ROS node, and it's got a whole bunch of nodes in there. I've got a custom node in there for dealing with my servo controller and also for the display, which you can't really see here. It's reading out the position it sees the object it's curious about, and also reading out how far away it thinks it is, some basic things like that. And it's also spewing out information on my little SSH.
Those aren't real eyes.
Well, okay, so a long time ago when I was here with this robot originally, there was a complaint, not enough robots named after women. So since this is for Robo Magellan, Robo Magellan. And of course, Robo Magellan has to have female eyes. So now watch. Check it out, man. I'm going to strut my stuff and it's watch. Oh yeah.
Oh yeah.
That's what I'm talking about.
Blue baby.
Thank you very much.
Okay.
Thanks, Mike. Hi everyone, I'm Bobby. Me and my team have a website that collects exoskeleton news. So exoskeletons are basically robotic devices that don't try to remove the human from the equation but augment the human. So the robotic device should be working in tandem with the human operator at all times. So we were collecting all of these articles and writing articles about how the industry is doing, what different applications there are for exoskeletons. And it occurred to us that it's really difficult to write about something that you don't have or you haven't touched yourself. So we came up with the idea to make a basic exoskeleton device made out of Lego NXT. So it's 12 Lego robots, which servo motors, which are horribly underpowered, but it still gives you a basic idea of what is compliance, what is power application, timing, all of the things that are plaguing the exoskeleton industry. So the website is exoskeletonreport.com. Please check us out. We have about 70 articles at this point, and we're always looking for other people that are interested in the exoskeleton industry to join us.
Excellent.
Everyone see this? Zoom in on this. Okay, this is, well, I'm working with Wayne on this. This is Wayne's baby. This is Loki. We have 9 of them that we're bringing up. I'm trying to bring up 5 of them. And so we have an Arduino Busino. It's basically an Arduino on steroids, has extra UARTs on the main board. Raspberry Pi, Wi-Fi dongle, Raspberry Pi camera. Polulu motors with encoders, magnetic encoders. So basically it's a fully functional robot that has an upward-looking camera for sealing fiducials. We also can supply it with a sonar array so it can do obstacle avoidance. So basically this is code compatible with the Ubiquity Robotics big platform. So my spiel is that there are millions of phone apps, but there would be 0 phone apps if the first thing you told the phone app developer is, first you have to build a cell phone. Okay. There are no robot apps because there are no developer platforms for roboticists. That's what Ubiquity Robots wants to do. This is going to be our low-end platform, $100 to $200. Hopefully we're going to start selling a lot of them after Makers Fair. And then if you want a robot that can bring you a keg of beer, you can move up to our bigger platform, having already written the code. Very good. Questions?
Show off different angles.
Sure. So Raspberry Pi camera, Lulu motors, you know, USB battery pack. I made an interesting discovery that the Lulu motors are not standard as to what their polarity is. So of the first 5 robots that I had, 2 went straight, 1 went backwards, and the other 2 turned in circles.
And I want to point out the most important feature of this. It's got a clever lever that you can just pick it around and carry it. Here you go. Okay. Andrew.
Is a BattleBot a robot?
Yes, it's a robot.
Okay.
Okay. Just you can't turn it on in this room.
There are children. Save the children.
Save the children. Okay. Looks we've got another robot coming.
I'll be on deck.
Yeah.
Go ahead. It's working.
So we last year put together a monster robot to take and pick up samples. It had a battery to let it run for 2 hours and weighed over 60 kilos. It didn't do very well. But then nobody else at the NASA Sample Challenge did very well either. So they're running it again this year. And so what we've just done is we've taken a tracked vehicle and we are actually, it's not going to be autonomous. It's going to be driven by another camera platform. It's going to track where it is and track the samples. But we're calling this a minion. And it's going to go out and basically pick.
Can you drive it over here so I can get it in camera?
So it has a stereo camera on it that will basically drive and take the last like 5-10 feet to get it to the object so it can pick it up. And then basically it'll be driven back home. It won't have to do really much by itself. It will have a set of fiducials that will be tracked by the camera system that basically sits on the platform. And right now, this doesn't show much because it looks like I'm joysticking it, and I am, but it's really a serial connection through the laptop. And so we can make an algorithm that will drive this. So we actually have a long-range serial connection that's making this joystick work. But it will be a ROS node that will actually drive this thing, taking the fiducial and saying, oh, match this to where the object is, and it will drive it there. So this is the start of it, and
we'll see more.
You'll see more.
Okay.
Hi everyone, I'm Andrew. This is my first meeting, so I didn't know. Yay! Yeah. Thank you. You've all been very strange. Yeah, so this happened to be in my car, but it's not as smart as any of the robots we've seen, but I hope that's okay. So this is a BattleBot. The way that it worked, this is a BattleBot. So this little BattleBot is 3 pounds, and the thing that is unique about it is that it was made for the. Put it down. I'll get it. Okay. Weaponized Plastic Fighting League. So that's a tournament where it has one additional rule, and on top of all the general safety stuff, that all the external parts of the robot and the weapon itself have to be made out of non-metal. So here this has been milled out of a single piece of high-density polyethylene, that's the chassis, and then it has polycarbonate armor, and the weapon is made out of garolite, which is a type of fiberglass. So right now it's been through a battle and it's pretty broken. What happened was that the motor, the bearings blew up and they kind of destroyed the inside of this motor, so I'll have to get a new one. But I just wanted to show that, and if this motor is the size of what makes a 3-pound BattleBot, maybe we'll have something to look forward to in the future. So that's just a sneak peek, and a bunch of motor controller boards. These are Benjamin Vetter's open source motor controller. So I'll be putting some of those together, and I'll have extra boards if people want to experiment with it. Come talk to me.
Is that a Hubless, brushless motor?
Yeah, so this is a brushless motor. It has Hall effect sensors in it, and it can do, theoretically, the hobby specs are like 4 horsepower, but you have to take those with a grain of salt, so let's say 1.
Is this for the Fetch League?
This little guy, yes, he was.
Cool. Very good.
Thank you.
It's like Joanna? Yelena. Come on up. And are there more robots? What? Okay. And any more after Dillo?
Hey, so just to mix things up a little bit, we have a little wearable robot for you today. This is a wearable quadcopter. Thank you, that's the end of the presentation. Drops the mic. So our intention here is actually a really practical device that is a personal photographer you can bring with you anywhere. Nixie is bistable. It is stable in this flat form factor, and like a slap bracelet, it quickly slaps onto your wrist. And the idea is, if you're having a special moment, you're like, oh man, it's my first presentation at Brew Robotics. It's a big deal. So you can literally just throw it, and I'm not allowed to throw it, so I'm not going to fly it here. But the device is perpetually in standby, so without pressing a single button, I throw it, it goes into free fall, catches itself, turns to face me, takes the photo or video and returns to me, and hovers until I grab it and put it back on my wrist. Thank you. Just to say a little bit more about it. So the idea is that even as you're moving throughout the day, it's sort of sensing roughly what you're doing, and it's continuously buffering the data. So when you throw it, it checks the buffer, sees how it was thrown, and it flies in the direction you threw it, and how hard you throw tells it how far to go. And so it goes a corresponding distance and turns to face you and returns, and then the act of grabbing it cuts the props for safety, and then you put it back on your wrist. So the whole round trip doesn't take a single button, and you go from thought to photo in about 2 seconds. So the question was Kickstarter. We want to make this actually like a real consumer electronics product. In my experience, sometimes when you go with Kickstarter, you play your hand a little too soon. So we're actually tuning the form factor and the features. And once we have it absolutely refined, we might do Kickstarter, but honestly mainly for the marketing rather than for the funding. Please.
I have to ask really quick,
Yeah.
just with it in standby constantly, how's the battery life?
So the standby is like a real-time operating system that's really, really low power, and so it's meant to have a full day's worth of use.
Very cool.
How does it know when you grab it or when it's on your wrist?
It doesn't need to know. I mean, so if I threw it like this, it wouldn't know and it would still try to fly, which is not ideal. But we think we can teach users to only throw it this way, right? We're also exploring ways that it could sense itself, but with something so small, weight is at a premium, right?
Does it indicate to you before you throw it that it's almost out of battery?
Yes. So another thing we're trying to do is keep the part the user has to think about really limited, but battery is obviously a critical thing. So please.
What about damage to the props if you're wearing that around all day?
So first of all, props are cheap and replaceable. They're going to get damaged no matter what, one way or the other, so we're going to have those easily replaceable. But with that said, also to the point of safety, the production model we ship is going to have propeller guards, right? Because we really want this to be something you would be comfortable using around your children. And then it's going to be much more protected even when it's on your person.
Price?
I can't tell you exactly, but it's going. But yeah, of course you have to ask. We're going to be competitive with GoPro at first, and then go down from there. Please.
If I'm wearing it and I trip and fall, will it fly away and take a picture of me?
We're going to work on that feature.
Let's do one more
That's
question.
a good idea.
How does it tell where you are when you throw it?
So that's the interesting thing. Thanks for asking that question. I don't know him. This is the first quadcopter in the world that we know of, and the only one that can do a full flight on inertial navigation alone. So it flies without GPS or machine vision. That whole round trip is inertial, which means that it goes out and actually turns to face the direction it was thrown from. Now we're adding machine vision to actually reduce the drift so you can have longer flights, and then it will recognize you by knowing where it was thrown from. But our goal is to not have to have a beacon and not have to depend on like GPS, because we want this to work indoors and high precision. Yeah. Okay. And also we're local and we're hiring, and Julie can get even deeper into the hardware than I can, so feel free to ask us any questions. Yeah.
I'm sorry to be cutting questions off, but we need to get our talk started.
Okay.
So they're going to be in back. You can ask them questions in back.
Yeah.
Okay?
Thanks, guys. Thanks.
Okay.
Don't have much to show, at least like to demo, but I did want to show you some progress. A couple months ago, I gave a demo of the smart lamp project that I was working on. I took it apart over the holidays and have kind of almost completely redone it. And so I decided that the camera is A, very heavy weight-wise, and B, the camera I was using doesn't really do a whole lot. It was a Pixie Cam. So the blob tracking really isn't the issue. What I found for the application that I was looking for, and we talked to a bunch of people here, is heat. So made it smaller using XL320 Dynamixels, and I have some pyrolytic sensors. So I found that just by hooking that up to an Arduino, it can detect my hand, it can detect my individual fingers versus the space between my fingers, it can detect the soldering iron, it can basically do everything that I wanted the optical version to do. So, and it's a lot smaller. So. And this is kind of, you know, getting more to like my goal of being able to like hang this over my workbench, or maybe off your shoulder, or just a bunch of different possibilities. And I think making it smaller has also really just freed up my, you know, design brain to. I've got some really neat ideas of like what I want to do with it. So it's 3D printed, some XL320 sensors. I did all of this in OpenSCAD, and that's pretty much about it. And I'll bring it back the next time I actually have something to show.